Dr.
Yes, thank you.
Thomas Prettyman from PSI. So Dr. Thomas, can you share your screen?
So I'm going to talk about carbon and organics on Ceres. This is going to be kind of a summary talk where I review the dawn and telescopic data and provide some interpretations. They're my co-authors, and work is partially funded by the Survey Toolbox for Research and Exploration project. So just to get started, looking at Ceres surface composition, Ceres has hydrated minerals that are pervasive on the surface, as can be seen in the chart on the right. The alteration assemblages that are globally distributed contain magnesium phyllosilicates, ammoniated clays, carbonates, and a darkening agent. And that darkening agent might be amorphous carbon. One key thing to understand about Ceres is that it's similar to the CI-CM chondrites, but they really do provide an imperfect analog for Ceres. And this is mainly because Ceres is large and it likely underwent extensive ice rock fractionation, producing a differentiated interior. And that would be unlike the CI-CM parent bodies. In addition to the hydrated minerals on the surface, there is water ice, and you can infer from data acquired by Dawn's gamma ray and neutron detector that you have a dry lag, albeit hydrated, covering ice at depth. Any elemental data that I show will be for the equator, where the measurements are less influenced by the subsurface water ice. Now, this is my summary chart for carbon. The background blue would be magnesium carbonates, which are all over the surface of Ceres. This is work by Carazzo et al. And then in certain regions, very concentrated in craters, for example, and in mountains, you have sodium carbonates. And the fact that you have different carbonates on the surface indicate that there were different conditions for hydrothermal processing within Ceres' interior and crust. So just making the rounds on the sodium carbonate deposits, these are bright features or facula. You have hydrothermal activity occurring in Akator, which could have been my impact heating, or brine sourced from the crust. You have extruded cryomagmas on the surface, such as Ahuna Mons. And you also have fresh impacts that reveal structures that might be brine plumes. In addition to all the carbonates that you see on the surface, you also see organics, which allow you to start to make some assessment of organocarbonate associations. And question endogenic or exogenic we'll get to in a second. But before that, I'll just mention that carbon itself as an element is higher than the meteorites in the global regolith based on grand observations, and a portion of it may be in the form of graphitized organics. So here are the Dawn Veer observations, and you can see here that places that are bright in the vicinity of Ernetit crater, which I showed you earlier, have enhanced 3.3 to 3.6 micron absorption feature, indicating the presence of organics. These are methyl functional groups associated with aliphatic hydrocarbons, so long chain hydrocarbons. These are also nicely associated with the carbonates, which appear to be magnesium rich in this region. Here's the case for endogenic origin versus exogenic. Very strong case for endogenic origin. One is just the association of the organics themselves with the carbonates and also ammonium-bearing compounds. This suggests that what you're looking at is the extrusion of cryovolcanic fluids. With the high-res framing camera data making association with organics and red slope, you can see that the pattern of organics could result from small impacts that are recent. This is work by Peters et al. And then finally, the kind of linchpin here is that it's just very inefficient to deliver organics by impact. So they very well might be endogenic. So UV spectroscopy provides more clues. On the right, we have data from Hubble. This is Hendricks et al., where we have normalized reflectance versus wavelength. And you can see in the far UV, there's this bump And this bump is associated with graphitized carbon species. And this could have resulted from organic molecules exposed to ionizing radiation. And then it produces, breaks bonds and removes the hydrogen, producing this bump. Further evidence for this comes from a model comparison where you have graphitized carbon comparing very nicely to the far UV Ceres spectrum. And this tends to imply that graphitized species are pervasive on the surface of Ceres. If that's true, then why didn't Veer see organic matter everywhere? And the answer is kind of self-evident, but verified by Kaplan et al., namely the strength of the 3.4 micron feature would tend to decrease with graphitization. So bottom line, organics may well be pervasive on Ceres, but not easily detected in the near IR. Grand observations are interesting because if you look at a plot of carbon weight percent versus hydrogen weight percent, you can see that the regolith of Ceres has more than 10 weight percent carbon compared to the meteorites, which are, and it's also less than comets. But this is still a really large amount of carbon. And the only way that we can think to explain it is that it's consistent with a differentiated interior. In other words, you had to have elemental fractionation and carbon species fractionation as Ceres formed. And this is consistent with geophysical data by Fu and Castillo and others. So it turns out also, a study by Marquis et al. Shows that surface chemistry and mineralogy can be reconciled if you have graphitized organics on the surface, and that kind of ties all the measurements together rather nicely. So one way to sort of discuss this is to look at the analog materials, and on the right I have a plot of carbon versus hydrogen for carbonaceous meteorites that have undergone aqueous alteration. And it turns out carbon's partitioned into organics, carbonates, and unidentified components. These are shown here. Here are the organics. The white is the total carbon, green is organics, and then the kind of magenta is carbonates. And it turns out that in these meteorites, carbon is primarily in the form of insoluble organic matter. But amongst the soluble component, you also have aliphatic hydrocarbons, similar to what you might find on Ceres. Now, to understand this even more, we have to understand production modification of carbonaceous materials on these parent bodies. And Schulte and Schock proposed that most of the soluble component really comes from coupled aqueous alteration and abiotic synthesis of aliphatic organic molecules. This is easy to understand how this could happen. When you have aqueous alteration, you have serpentization. It's an exogenic process. It produces heat. And many of the reactions produce hydrogen gas, such as the one below. And then this thermal energy, plus the presence of accreted carbon species and high hydrogen fugacity can result in abiotic synthesis, such as in the reaction shown below. The flip side of the coin is carbonates. To make the carbonates, you can have oxidizing conditions in the hydrothermal system that eat up the organic matter, producing CO2 gas that combines with water to make carbonates. And you can see this rather clearly in the chart below, where for selected CM chondrites, you have increasing carbonate to IOM content with alteration. And this is a study that was done by results presented by McSween et al. In 2017. In addition, carbonate composition changes with alteration. The point of this is that the meteorites and Ceres really should provide a test bed to understand the different conditions under which organic matter and carbonates can form. Okay, and then one thing that everyone should be aware of is the meteorite Z. It's an H chondrite that contains exogenic materials in the form of halite crystals, and it turns out these halites contain organic matter, and these may have been made in hydrothermal systems very similar to that of Ceres. The bottom line is asteroid interiors can host environments suitable for prebiotic chemistry. That said, all of this places Ceres as an extremely nice looking astrobiological target. And it also falls on the spectrum of ocean worlds. You have all the elements necessary. energy and water to do prebiotic chemistry. It's really cool. So to sort of wrap things up, this is the exploration connection. The Ceres studies and future missions should provide insights into crustal processes and hydrothermal evolution of water-rich asteroids. It also provides a testbed for different concepts in astrobiology. The specific studies we were working on support Survey-Trex themes, namely use of UV to identify carbon-rich asteroids and improving the integration of optical and nuclear remote sensing methods. And then finally, there's a potential both on Ceres and in water-rich asteroids for ISRU via extraction of water and production of propellant via methanation. And that concludes my talk. Thank you.